All right, welcome to part 2 of Measurement Foundations. If you have not watched the first part, go back and watch part 1 of the notes where we talked about measurement types, estimation, and significant figures. In this video, we're going to recap sig figs and then hit scientific notation. So if you will go with me in your packets to this page here, this is a little significant figures practice. And it also has a little challenge as part of it. I kind of explained that in class. So reread the instructions to kind of figure out what you're doing now that you actually have a better idea of what significant figures are. Keeping in mind those rules we talked about. So basically, placeholder zeros, not significant. Anything that's part of the measurement, meaning it's a non-zero number, or they're sandwiched zeros, or they're zeros following a decimal point, or like at the end of the value, including a decimal point. Those are all part of the estimation. So I'm going to just kind of help you get started on writing out some significant figures. So our values here are in these little dials, and I just want you to write in the blanks how many sig figs there are. So I'm going to do a couple of these with you and then set you loose to work on the rest. If you're still struggling with these, then I can help you with them on the Zoom on Thursday. So let's go ahead and start here right at the top, 60.00. Notice there's a decimal point, so that makes all of these final zeros significant. Just like in the digital scale example that we looked at with 65.00. So this number has 4 significant figures. All 4 of them are part of the estimation. Put that in the line. Okay. 80. The 0 in the tens place here is just a placeholder. It's not significant to the estimation. So there would be only one significant figure in the number 80. 0.1. The 0 in the ones place is a placeholder. That means we only have one significant figure. 6,030. Well, we have non-zero numbers and a sandwich zero. All of these are significant to the measurement. And we also have a placeholder 0 in the ones place. So that means the 0 at the end is not significant, but the other 3 are. 3 significant values to the measurement. Okay, I'm going to let you continue working on these, thinking about placeholder values. They're either going to be at the very beginning, like this, those are placeholder zeros, or at the very end without a decimal point, so like these here. Okay, so those would be placeholder zeros. Examples of not placeholder zeros. This is not a placeholder 0. Those are significant because there's a decimal at the end. These are significant because there's a decimal at the end. All right, so use that to help you track significant to the estimation values. You are going to fill in the number of significant figures in each of the lines around the outside, and then you'll use that to help you crack the code. Anything where you wrote a 5, those letters, you will take and unscramble. That'll be your first word. And then the ones that have 4, you'll unscramble those letters that are around here, and that'll be your second word. And then the 3s, so like this is a 3, you'll use that. Unscramble all the 3s, and then you'll do the same for the 1s. So these would be part of that last word. A 4-word response to our never trust a blank, 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 blank. And that's a 4-letter word. That are these 4 letters that have stars next to them. Okay, so there's your little code. The other assignment to go along with what we talked about in part 1 is this graduated cylinder practice estimation. So you'll go in and you'll record all of the values you know for sure, and then estimate one value based on the tick marks that you, the last 2 that you know, and make one estimate. So you'll do that on these graduated cylinders for practice on estimation. All right, let's jump into our last part of these notes, scientific notation. Now, when we're working with scientific notation, we want to be able to rewrite numbers that are really, really big or really, really small, so we don't have a ton of placeholder zeros, because we already talked about placeholder zeros are not significant to the estimation. So if we can, let's just cut them and make it as short as possible so that all we're left with are the significant values. So our scientific notation, we're going to define that as rewriting very large or very small numbers, specifically measurements. And we're going to do that as numbers between 1 and 10, so that we're cutting out all of our placeholder zeros, multiplied by 10 to an appropriate exponent. Okay, if we have a really, really small number, then our exponent is going to be negative, like anything that's a fraction, smaller than 1, negative exponent. And if it's a large number, it'll have a positive exponent. Okay. When I say small and large numbers, I'm talking about the standard notation of the number. For example, if I have 500, that would be a large number, so when I put my exponents in, it would be positive. If I have 0.005, now that's a small number, my exponent is going to be negative. When I do my exponents, I'm going to figure that out based on how many times I've moved my decimal point. Let's look at some examples so that you can see how this works. Example 2 says, determine the number of significant figures in each measurement, then write it in scientific notation with proper units. So our first is a digital reading from this stopwatch, so we don't need to do any estimation. It's already done for us digitally. However, we do need to identify our significant figures. So notice our starting zeros here, those are just placeholders. So we have 2 significant figures, and we want to write this in scientific notation. So what you'll do is you'll take your decimal point and you're just going to swoop it and count how many times until you reach a number between 1 and 10. So I'm going to move it to the right until I get between 7 and 6, so that it's 7.6, a number between 1 and 10. 1, 2, 3 times to get there. So I've got 7.6 times 10 to the third power. Now I need to decide if it's going to be negative third power or positive third power. Well, was the standard notation of this number really large or really small? It was really small. So that means it's a negative 3. Negative 3. This is also communicating to the reader that when you turn it back into standard notation, you're going to be moving it to the left. If it was positive, to turn it back into standard notation, you would move it to the right. There's our answer. Let's look at this beaker here. We've got tick marks telling us by 50s how much is in the container. So first we need to make an estimate of the volume in this beaker. It's definitely between 100 and 150, so we can put our 100s place, we know for sure. Now we need to estimate our tens place. Somewhere between 100 and 150, I'm going to estimate the tens place to be 40 milliliters. Now, hopefully this will become clear with this example why the 0 is not part of the estimate. It is a placeholder, but we really estimated this 4, not the 0. So we say the 0 is not significant to the estimate. It's just a placeholder for keeping that value consistent to how much it is. It's not 14 milliliters, it's 140 milliliters, but we estimated the tens place. So the 0 there is not really significant to this estimation. Therefore, we would say this only has 2 significant figures. In order to write this one in scientific notation, I'm going to take that assumed decimal point after the ones place and move it now, this time to the left, 2 spots to make it 1.4. So 1, 2, 1.4 times 10, we moved it twice to the second power. And our standard notation is large, so it's positive 2. And again, this is communicating that written in scientific notation. In order to turn it back to standard notation, we need to move it twice to the right. Positive is telling us move to the right. Negative is telling us move to the left. Okay. And notice I did not keep that 0, 1.40. I did not include that because we still want it to have 2 significant figures. If I add the 0, now I have 3 significant figures is what I'm communicating to my reader, because it would be following a decimal point. Let's do this length measurement here. We do not need to estimate this time, it's just been given to us. So our number here is 1,859,000 meters. So what this number is communicating to us is that the thousands place was estimated, and now we have these placeholder zeros that are not significant. Therefore, our number has 4 significant figures to the estimation. The rest are just placeholders. Always look for those placeholders. Those are the ones that are not part of the measurement. Now let's write this in scientific notation. Start with putting your decimal in, and now let's move it until it's 1.859. So we're going to move it 1, 2, 3, 4, 5, 6 times, and we include all those significant figures, but then you can drop the zeros because they're not part of the estimate. 1.859 times 10 to the 6th power meters. There you go. You know that it's positive 6 because our standard notation was a large number, 1,859,000. And lastly, we have a scale here, some grams. These zeros in the front are placeholders. So our estimated value was this 1 at the end. So that means the 7 and the 3 we knew for sure, and the 1 is estimated based on this scale's capabilities. So that means we have 3 significant figures. And to write this in scientific notation, we take the decimal, move it over 1, 2, 3, 4 times to get to 7.31 times 10 to the 4th power. Is it positive or negative? This one is negative because our standard notation was a really tiny number. So it's negative 4th power grams, since this is on a mass balance. Okay, so there's scientific notation. Count how many times you move the decimal, and then think about, was the standard notation really tiny or really large, to figure out if it's positive or negative.